The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's Tech Talk on intermediate topics in direct digital control systems. My name is Sherry Adams, and I will be the moderator for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. When you first joined the Tech Talk, an attendee control panel appeared on the right side of your desktop. On the left side of the control panel is a small tab with an arrow icon at the top. Pressing this icon allows you to minimize and maximize the control panel. When maximized, you can use the control panel to submit questions. We will gather your questions throughout the Tech Talk, and we will leave a little time at the end for Q&A. If your question is related to a particular slide, please indicate the number of that slide in your question. A PDF of the slides from the presentation will be sent out electronically to all those who have registered for today's Tech Talk. We will also be recording this Tech Talk, and it will be available on our website under the resource section. There is a new password to access the Tech Talks, and it will be emailed to you after this presentation. Today's presenter is Steve Alschuler. Steve is originally from Chicago area. He went to Ohio State University for a bachelor's in mechanical engineering and graduated in 1992. He spent a year with Train Air Conditioning, then 4 years with Johnson Controls. He later owned a controls contracting firm which designed and installed Johnson Controls Meneses DDC systems throughout New Mexico and West Texas. In 2007, he switched to consulting, engineering, commissioning, and has been a commissioning provider ever since. So welcome, Steve.
Thank you. Thank you, Sherry. Thanks, everyone, for tuning in. I know controls is a big issue in the commissioning business. It is certainly in our business. So I wanted to put together this presentation and kind of cover some more intermediate/advanced topics beyond the basics. So with that, I think we're ready to get started. We're going to talk about the basics of a control loop. For some of you, this might be a review. For others, it might be a good refresher. And then some of the issues with the types of inputs and outputs that we see. We're going to go through the algorithms used in controls. We're going to start basic with a simple PID. We're going to get into cascaded loops and some of the different software functions. Staging of chillers and boilers and pumps, which is all too common, and a lot of issues there. Backnet integration, there's always issues with backnet integration. We'll talk about some of those. Then we're going to talk about why, in my opinion, the controls industry is kind of broken and what commissioning is doing to fix it. And then if we have time at the end, and this is my first time giving this presentation, so I haven't timed it, but if we have time at the end, I have screenshots from some of our jobs at Bath that shows you the type of stuff we discover every day when we commission projects, both new construction and existing buildings. So with that, let's start with the basics. How do controls work? Well, it all goes back to a control loop. There's three parts. There's the sensor, which senses a variable like temperature, pressure, or humidity. The sensor is connected to the black box. And the black box connected to the control device, which could be a valve or a damper or a mechanical piece of equipment like a boiler, a chiller, or a pump. Sometimes what you're controlling affects what it is you're sensing. And if that's the case, it's what's called a closed loop. Sometimes what you're controlling has no effect on what it is you're sensing. So if you're sensing room temperature and you're modulating a chilled water control valve on a fan coil, obviously, the air coming into that room is cooler and that changes the room temperature, so that would be a closed loop. If you're sensing the outside air temperature and you're going to turn the boiler on when the outside air falls below 55 degrees, no matter what you do in that building, you're not going to affect the outside air temperature, so that would be an open loop. When we talk about the algorithms and loops, I always like to use the analogy of a loop of me taking a shower. That's picture me before my P90X exercise program. But the way I take a shower every morning is I sense the water with my left hand. So my left hand is effectively the sensor. And then I decide if the water's too warm or too cold. So my brain is analogous to the controller. And then I reposition the faucet, which is a controlled device. And then as soon as reposition a faucet, of course, that changed the temperature, and I have to repeat that process. And that's the same process that's used in DDC controls. That process, the last time I checked, which is several years ago, normally takes place every second. So the control smarts is sensing the temperature, executing the algorithm, and repositioning the output device once a second. For PLC controls, that could be a tenth of a second or even quicker. But for HVAC, once a second is plenty. Okay, the types of inputs and outputs used by controls. Analog means that there's an infinite number of values, like temperature, pressure. The most typical types of inputs are a thermistor or a resistance temperature detector. I'm not sure. I know there's a difference between them. I always get confused what that difference is, but it's kind of insignificant. Those are passive devices that their resistance changes in proportion to temperature, and it's not necessarily a linear response. And then there's active analog inputs, and the most common ones are 0 to 5 volts DC, 0 to 10 volts DC, or 4 to 20 milliamps. And then on the output side, you also have analog outputs, same format, 0 to 5 volts, 0 to 10 volts, and 4 to 20 are the most common. There's a few others that are rarely used. And then the other type of input, I use binary and digital interchangeably, as most people do. You can have a dry contact, which is just something that when the device goes from open to closed or closed to open, on to off, then the contact closes and the controller can sense that the contact's been closed, and that's how it knows that the device has changed states. So an example might be a filter differential pressure switch. There's like a diaphragm that is being pushed by the air pressure difference before and after the filters. And when the diaphragm makes contact, it brings those two pieces of metal together, and now the circuit's complete. And that's how the control system knows that the filter is ready to be changed. A current switch that senses current works in a similar fashion. Those aren't active. They don't have voltage. That's why they're called dry. So they're making a circuit, but they're not putting out voltage. You can have binary digital inputs that come into your controls with 24 volts or 120 volts. Not as common, but they still qualify as both binary or digital inputs. Outputs, same concept. You can have a dry contact, or you can have a 24 volt output or 120 volt output. Okay, what are the issues as commissioning agents that we should be looking out for when we deal with inputs and outputs? Scaling is often an issue. So you might have output or an input coming in, and let's say it's a CO2 sensor. And well, let me start with the example. So when you see the output going to a valve, whether it's a chilled water valve or a hot water valve, 100% should mean fully open, and 0% should mean fully closed. Okay. Now, occasionally, controls contractors will use what's called a normally open valve. Okay, which means that when there's no power to that valve, it's in the open position, usually because of a spring. Okay, and this comes back from the pneumatic days when valves always had a normal position. They had a spring and a diaphragm. Okay. If it's a normally open valve, that means when you're sending at 0 volts, it's in the open position, and when you're sending at 10 volts, if it's a 0 to 10 volt device, it's in the closed position. Well, some controls contractors don't change the scaling in their system. So when they're sending at 10 volts, that's 100% output, and 100% output to a normally open valve will means it's closed. So on the graphics, if you're looking at a normally open valve, you don't know it's normally open, and you see 100% output, that means it's closed. Don't let them do that, okay? That's something that, as a commissioning agent, I would not accept, because they could rescale that so that even though 100% output means it's closed, it can show on the graphic as open, which is how it should be, okay? So that's an issue of scaling that can be easily corrected that you should look out for. In that example, chilled water valves. When you have inputs like CO2 sensors, you've got to confirm that if it's a 0 to 10 volt device And CO2, that CO2 sensors, let's say 0 to 2,000 parts per million, that they put in 10 volts means 2,000 parts per million. If it's a CO2 sensor that's 4,000 parts per million and they didn't put in that upper value, when you get a full signal or a half signal, it's not going to read right in the controls. So it's very easy for a controls contractor to mess up the scaling, and that's going to mess up the calibration of the instruments, or how, at least how they read within the system. Also, thermistors are generally not interchangeable between manufacturers. So if you have an automated logic control system and you're putting it, you're replacing a Johnson system, they most likely are not able to reuse the thermistors, because the Johnson thermistor has a characteristic curve that's nonlinear that the Johnson controls is familiar with. And as the resistance of that thermistor changes, Johnson knows what that curve looks like, so it knows when the ohms are this, the temperature is this. ALC has their own thermistors with their own characteristic curves. So you got to make sure that the thermistors used match up with the controls that have the characteristic curves for that thermistors. Flow transmitters, flow stations that use differential pressure. If you have a pitot tube flow station in the outside air duct, for example, Air Monitor is probably the most popular brand, and you're using a differential pressure transmitter, remember that the pressure changes to the square of the velocity. So the algorithm that's in the control system has to do what's called a square root extraction. It can't directly read airflow with that differential pressure transmitter. It's not a one-to-one relationship. So again, that's kind of an issue of scaling. Making sure the units are right on the graphics. You know, I've seen jobs where the airflow measuring station reads in feet per minute. That doesn't help anybody. Nobody cares about the feet per minute of the airflow. They care about the CFM. So that needs to be scaled correctly. VFD output, I don't think it should read in hertz. I think it should read in percent. Is the pump at 100% or 20% speed? Not everyone, that's not always 60 hertz. You might overspeed the pump. Okay, talking about differential pressure transmitters, this is a question we use on our entrance exam at our company to see how well people know controls. If you have a differential pressure transmitter, like a Citra is one of the most common brands, the error is not the percent of reading, it's the percent of full scale. Okay, and that's an important thing that a lot of people don't realize. So it's very important that you select the differential pressure transmitter close to the pressure it's going to see. So these things can be purchased in 0 to 1 inch, 0 to 2 inch, 0 to 10 inch. If you got a 0 to 10 inch differential pressure transmitter and you were using that to read building pressure, you're going to have a really large error, because if it's plus or minus 1%, again, that's at full scale. So a 0 to 10 inch differential pressure transmitter is going to be 0.1 inch off no matter what it reads. And of course, building pressure is typically 0.1 or 0.05. So it's going to be 100% off. Just kind of an important thing to understand, differential pressure transmitters, the accuracy is percent of full scale, not the percent of reading. All right, let's get into the math behind controls. People throw out the term PIDs. Do you really know what a PID is? And can you describe it? Do you know well enough to describe it? Okay, we have a room. It's supposed to be 72 degrees. Okay, this is your house. Okay, you have a furnace. Most likely, you have a thermostat in your living room. Okay, some exceptions. You might have radiant heat, but bear with me. The type of algorithm used on a residential furnace 99% of the time is a two-position algorithm. So the furnace is either on or it's off. It's a binary device. It's not an analog device. And because it's a binary device, it could only be on or off. So your room gets cold, turns on, warms up, turns off, turns on. This is two-position control. It's the least sophisticated. Okay, the next level is proportional control. With proportional control, the device is now analog, and you are, let's say it's a fan coil serving the space, and the space temperature is 72 degrees, and that chilled water valve can be anywhere from 0 to 100% open. Well, if the space is, let's say, 74 degrees, how much open is that valve? Is it 100% open or 50% open or 20% open? With proportional control, the amount open or the amount of the output is proportional between the difference between the set point and the actual temperature. So if we said that we had a 4-degree proportional band, that would mean that that chilled water valve would open 25% every degree we go away from set point. So 73 degrees, it'd be 25% open, 74 degrees, it'd be 50% open, like that. That's what pneumatics use for the longest time. The next level is PI control, or proportional plus integral. This is what most DDC systems use in their loops. They call them PID loops, but they usually don't use a derivative. We'll show that next. With proportional only control, you actually never get to set point. That's how the math works. Because at 74 degrees, if that valve is 50% open, okay, and the thermal load just exactly balances to that valve being 50% open, that valve, the algorithm isn't smart enough to go, you know what, I'm not getting the set point, I need to increase my output. That's where you get to proportional plus integral control. Now, integration, the area under the curve for mathematics, the algorithm is not only has a proportional output, but it's looking at whether there's a positive or a negative area under the set point over time, times the x-axis. And it will increase the output if you're up here or decrease the output if you're down there. This is where you can actually get right on set point, okay? And again, this is what 90% of the loops within direct digital controls use. The last one's derivative. You get an even better response, derivative being the slope of the curve. Now the algorithm is not only looking at the area under the curve, it's also looking at how quickly you're approaching set point. If it sees you're approaching it too quickly, like you were in this slide, it will back off on the output. So this is your best response, but it's harder to set this up because you have to set up the integral and the derivative terms, and they kind of fight each other. The controls contractor is responsible for setting up these different values, the proportional term, the integral term, the derivative term. That's all done at the time the controls are installed. That cannot be modeled. That's not something that an engineer can model to get what the numbers should be. It's a trial and error process. That's the only way to do it. Some of the control systems have automatic loop tuning where there's an algorithm within the controls that supposedly find those numbers over time, like a self-tuning algorithm. But nevertheless, these are this is what happens if loops are not properly tuned correctly. You can have hunting and cycling, or it can just never get there. Okay, cascaded control loops are where you have a control loop and the output, a regular loop, the output is the control device, like a valve or a damper position. With a cascaded control loop, the output becomes the set point of another loop, okay? So you have a sensor algorithm, the output is the set point, and now you have a whole nother algorithm, and then you have a control device. The best example of this, you may not realize it, is a typical pressure-independent VAV box. So the sensor is sensing room temperature, okay, and then there's a PID algorithm that says what's the difference between room temperature and room set point. The output for pressure-independent is not the damper. The output is the airflow set point based on the difference between room temperature and room set point. Now that airflow set point goes into a separate control loop to control the damper within the VAV box. That's referred to as a cascaded loop, where there's a loop that sets the set point of another loop, okay? Oh, looks like I already had a slide that describes it. A pressure dependent, like a train tracker or those type of systems, it's pressure dependent because it's just one loop that's controlling that damper position. So as the other dampers within the system go to various positions, the pressure in the ductwork changes, and this system isn't smart enough to compensate. The damper is set at its position strictly based on the room temperature and the room set point, nothing to do with the pressure in the ductwork. Whereas with the pressure independent, you always have that little flow cross ring, and you're actually modulating the damper to maintain an airflow set point, and that airflow set point is determined by one of the loops. Okay, tuning is, we kind of covered this with this slide here of what happens if things aren't tuned correctly. It either cycles or it never gets there, okay, and this is the type of response you want. All of these things need to be set. proportional band, integral term, and if derivative terms used, it should be set. The only time I recommend using this is in static pressure control loops. That's a very fast changing thing where if you change the speed of the fan, the ductwork pressure changes just about instantaneously, certainly within a second or two. So when you have something where there's very fast changes, that's when you would use a derivative. Pretty much everything else in HVAC would only be a PI control loop. You'd set the proportional band, you'd set the integral term. The bigger the proportional band, the slower the response. The smaller the proportional band, oftentimes called the gain, the faster the response. The bigger the integral term, the faster the response. The smaller the integral term, the slower the response. Okay, software functions, and I'm looking at our time, we're moving quick. The PID loops usually reside in a controller at the piece of equipment. Software functions can be software programming that resides at the controller or at an upper level controller. Simple software functions, if then. If the outside air is less than 55, then start the boiler. If the lead pump is 90% or more, start the next pump. That would be a simple if-then software function. Another software function is high select, low select, and averaging functions. So you might have mixing dampers at an air handling unit. You have a PID loop trying to control the mixing dampers to maintain a minimum outside air flow for ventilation. So the input is outside air flow, and then the algorithm tries to control the mixing dampers. But that same mixing damper also might be tried to control for the economizer. So now you have a mixed air temperature sensor, a completely different control loop, that's still trying to control the same output, the mixing dampers. So you can have both loops running, and you can use a high select function. Whichever loop wants the outside air dampers to be open more, you pass that output through to the dampers. Okay, that'd be a high select function. You can have a low select function where you have a ductwork coming out of an air handler that splits and goes in two directions. And because it's going in two directions, you have two duct pressure differential pressure transmitters, and you want to modulate the speed of that fan for whichever one is lowest, right? And that might change over time as the sun goes from one side of the building to the other. So again, you kind of have two loops because you have two different sensors going into two different algorithms, and then whichever loop is higher, well, you're taking a low select, or you have one loop and you're selecting whichever input is lower and running that loop with it. That'd be a low select. You might have averaging where there's two space temperature sensors, like for a gymnasium. Gymnasium's a really big space. You might have a temperature sensor on each wall, and you're going to take an average of them to determine space temperature. Okay, more software functions, reset functions. Reset functions might be hot water supply. You go from 180 to 140 degrees as the outside air temperature goes from 20 to 60. So you're changing a set point based on some other parameter. In this case, you're changing the set point of the hot water supply based on the outside air. Resetting duct static pressure is a new energy saving trend. I guess it's not new anymore. I'm dating myself. But you might reset the duct pressure from 1.8 inches to 1.2 inches as the most open VAV box damper goes from 95 to 55. Different alarms you might have, the status and the command don't match. There's a variable is out of limit, like the supply air temperature is supposed to be 55, and if it's 5 degrees high or 5 degrees low or more away from that, then you have an alarm. Binary input might be a filter or an emergency power off, and then there's all kinds of backnet integrated alarms. Trend something over time, usually variables. I like to have 4 variables on a trend, 4 graphs at once. So I might have space temperature, space set point, outside air temperature, and outside air humidity, something like that. It's good to have define what your trend interval is. I like an hour. Capture the data once every hour. AHU with 3 PIDs controlling one device. This is back to the mixing dampers. If you throw in a CO2 sensor and you're going to modulate the mixing dampers, not only based on minimum airflow and turn economizer mixed air, but also modulating to maintain a CO2 in the space, you can have 3 different loops running at once and you're going to high select whichever output wants that damper to be open the most. Okay, chiller staging. A lot of engineers don't know how to do chiller staging. There's different ways to do it. You can do it based on supply water temperature is when you turn them on. So when you can't maintain 45 degrees, you bring on the next chiller, 40, let's say it's 47 degrees or more, bring on the next chiller. Or if you know the percent load of the chiller, either through BACnet or through an analog current transducer, you can bring them on when the first chiller is 90%, you bring on the second chiller. Bringing them on is easier than bringing them off. How do you turn them off? You cannot use supply water temperature to turn off a chiller. Okay, if you have two chillers on and your set point's 45, the chillers have their own controls. So even if they're 20% loaded, they're going to make 45-degree water. Okay, you can't turn off chillers with supply water. You can do it as the delta between supply and return or percent load. There's a few other ways, but we're not going to get into them because they're kind of advanced. Pump staging. Bring on the second pump when the first pump is 90% or more. Turn off the second pump when both pumps are 40%. So you have a pump running at 90%, you bring on the next pump when they're both running together, and you modulate the VFDs down to 40% or less, and you turn the extra pump off. And there might be more than two, but I'm using two. Okay, BACnet integration. The good news is it never works. The bad news is it never works. Why is it good news it never works? Because that's why we're all employed. We got to make sure that it works. You have to define what's being communicated, okay? And this is something that almost never gets written down. Just because it's BACnet integration, what does that mean? What objects do you want to see out of that chiller? Do you just want to see it, whether it's enabled or disabled? Or do you also want to see entering and leaving evaporator water, entering and leaving condenser water? Do you want to see the refrigerant pressures? Because that's going to be available through BACnet. That should really be determined at the plans and specs level by the consulting engineer. It should also be in the controls contractor's submittals, and it should also be in your functional test to verify every object that's supposed to be communicated between the BACnet device and the control system is there. Some of those are going to be read-only objects. Like if you have a chiller, you're only going to be able to read the refrigerant pressures. That's not something that a control system would control. The chiller controls that. And then some of them might be writable. So you might be able to write the leaving chilled water supply temperature from the control system. You got to test them, okay? You got to test them. Okay, this is what one of our functional tests looks like. We always have 5 parts to every test. I'm an ex-controls contractor, as Sherry indicated, and went into commissioning. A lot of what I do is controls related. We start with a point-to-point. We check every input and output. We check every software function. Remember, most of these software functions are custom written for the project. And what do we know about version 1.0 software? It's going to have issues. So you got to check every software function. You got to check the graphics. Graphics get mapped wrong. Room 102 shows up on the graphic as room 206. So you got to check that stuff. And then all the alarms that are supposed to be there. Is the variable under or over value? Is the pump on when it says off? Is the pump off when it says on? All of those need to be checked. And then trends help. If you tell the controls contractor what to trend, that helps prove the system. Okay, here's the issues with the controls industry today, okay? And I always joke the only difference between a controls contractor and a commissioning agent, having been both, is when I was a controls contractor, I was yelling at my own guys to get things right. Now I'm a commissioning agent, I yell at somebody else's guys. Controls almost never work, and it starts at the design. I'm in the Colorado, New Mexico, Texas markets, and pretty much all the time I see control systems are not designed correctly, okay? And then the controls contractor copies the design verbatim and puts it in their submittal. So now, not only is design incorrect, the submittal's incorrect, then it might get installed correctly because whoever goes out there looks at the design submittal, recognizes it would never work, and they just do their own thing. That's the norm. Or maybe they don't, and they put it in incorrectly. And then nobody gets accepted because nobody knows how it's supposed to work anyways. And then it gets operated incorrectly. So the industry's answer to this isn't to get better controls contractors. No, the industry doesn't want to do that. The industry says, let's just hire a second controls contractor to look over the shoulder of the first controls contractor, and that's what I describe myself as a commissioning agent. So the first thing we do is we make sure to help the engineer design it correctly. Then we make sure the submittals are complete, accurate, testable, and verifiable. If the submittals are not right, we have to get the submittals right. Otherwise, how do you pass or fail functional testing? You have to compare the actual building to approved submittals. So very important to get the submittals right, even if that takes several iterations. Then we verify and document proper installation. Most important thing, we test every aspect of the control system. The point-to-points, the loops, the tuning, the software functions, the graphics, the alarms, and the trends. And then we make sure that proper training and documentation occurs so they can operate it. Okay, I'm running out of time here, so I'm going to probably cut this short. This was a kind of a funny story. I'm going to show two stories. This is a design issue. Actual job in Texas and San Antonio. Economizer, when the outside air is 52 degrees, the unit shall be allowed to go into economizer. Okay, so it's implied that at 52 degrees, it's in economizer. It actually says shall be allowed, but that's how the controls contractor interpreted it. So if it's 52 degrees or less, it's in economizer. Heating mode, the zone temperature shall monitor the zone temperature sensor shall monitor zone temperature. On a call for heating, the unit supply fan, heating cycle shall be enabled. The heating mode is enabled whenever economizer is disabled. Okay, so this says the heating mode can only come on if the economizer is disabled. This says the economizer is automatically enabled below 52 degrees. Well, guess what? These schools were cold in the morning. Well, why were they cold in the morning? Because it was below 52 degrees, which meant the economizer was enabled, which meant heating was disabled. Here's a rooftop unit. If you have a rooftop unit serving a commercial space, the fan has to be on. It can't be on auto because you can't cycle the fan and maintain your ventilation requirements. Well, I'm looking at the time, and it's unfortunate because I have all kinds of fun slides of stuff that we find in jobs. I guess I got a couple minutes. I'll just show you. I'll show you one or two of my favorites. Where's one of my favorites? This is my favorite. This is a job that we were commissioning elementary school, and we looked at the boiler plant in another school that we weren't commissioning that we had access to through the control system. And I do that a lot. I just look and see how things are operating. Here's 3 boilers. This boiler 1 is enabled, and 140 going in, 151 going out, 11 degrees of heat is being added. This boiler 2 is disabled, but still 7 degrees are being added. But this boiler 3 is disabled, and 18 degrees of heat are being added. So these are the type of boilers you want on your projects because they actually work better off than they do when they're on. And those are the most energy efficient boilers out there. Those are the kind you want. Buy these. All kinds of other silly examples like that, but I'm out of time and I do want to open it up to questions because it's after 12:30. So with that, if you want to turn on the questions and see what people got.
Great, Steve. Thank you. We really appreciate your time and expertise. And actually, we don't have a question yet, but we'll give everybody a minute or two to submit a question. If you have one, please do so. In the meantime, while we're waiting for that, just as a reminder that registration is open for this year's annual conference, September 25th, 26th, and 27th. In Schaumburg, Illinois. Check out the website for some exciting things that will be happening, as well as some email announcements that will be coming out very soon. Okay, Steve, it looks like I do have a question, and it says, can you continue with your examples?
Can I continue? All right.
Yes, I think
these are
fun examples. And show some, of your real world examples, I think is what people would like to here. So go ahead and
all right.
We've got a couple more minutes.
All right. This is an airport in Texas. We tested this. You can't see the top of the slide, but it was about 95 degrees. We tested it in the middle of the summer, I think last summer. The boiler plant was shut off. The pumps are off. Okay. And the boilers had hot water temperature sensors, and looking here, this temperature on this hot water loop that's off because it's 95 degrees in El Paso, Texas, shows that it's 20.5 degrees. So I said, wow, somebody get a better run out there and make sure that pipe doesn't freeze. No, I'm being sarcastic. Obviously, it wasn't 20.5 degrees, but all you got to do, for me, my expertise, all I got to do is pretty much look at any control system anywhere, and I find these examples, even if they were commissioned by our competitors. This is another project, I think, in El Paso. This has a CO2 sensor, and the CO2 sensor is supposed to open the outside air dampers between 20 and 50% based on the CO2 level. And where is the CO2 level? What's going on here? Oh, okay. So this is a mixed air example. So we have outside air coming in. It's 89 degrees outside. Okay, outside air is coming in 89 degrees. Return air has got to be around 70, 75 degrees. Yet somehow the mixed air is 58 degrees. How is that possible? How do you mix 89 degree air with 70 degree return air or 75 degree return air and get 58 degrees? Here's a classic example. Chilled water and hot water valves both simultaneously open. Okay, rule number one in energy conservation, don't have heating and cooling going both at the same time. This looks like a tuning issue. Okay, you have, you're jumping all over the place. So the tuning on the loop is not good. What's going on here? Okay, this is a staging issue. This is our airport again. They have 3 air-cooled chillers. The water's going out at 48. It's coming back at 43. So it's actually like a 5-degree delta. Why are they running all 3 chillers? Okay, here's the deltas across the chillers: 3 degrees, 3.8 degrees, 2.8. It'd be much more energy efficient to just run one. You don't need 3 chillers at 20% load or 10% load when you can have 1 chiller at 80% load. Be much more efficient to do it that way. Okay, here's another mixed air example. I think you got supply air. Oh yeah, this is mapping. So 65 degree air coming back from the return. Outside air, I don't know what it is. They don't send it here. Oh, there it is, 62. 65 degree air coming back. 62 degree air from outside, and somehow they mix together before the coils, and it's 120 degrees. That's a neat trick if you can do that. But then after it goes through the coils, it cools back down to 61. So I think what happened is this sensor is actually there, and that sensor is actually there, and they have them shown wrong on the graphics. And then I already covered my boiler. Here's my favorite one, the boiler that works better when it's off. And I probably have enough material to do 8 hours on these kind of errors. Most of them, a lot of them we find during commissioning. A lot of them we find just give me an hour in front of your client, and I can do this for just about any client. I think there's been one instance where I looked at a control system and I didn't see these kind of errors. So virtually every control system out there, if you give me an hour, I'm going to give you a slide presentation just like this. All right, you can reach me here if you have further questions. If Sherry has any questions coming in, I'm happy to answer anything.
Yeah, Steve, if we could get maybe one question in that came through. Everybody wanted to see your examples. A lot of people did, but we did have a question that came through that I'd like to ask. And then to everyone out there, just a side note that is asked about whether you'd be getting the slides of this presentation. Yes, we'll be sending out a PDF. Also, this has been recorded and will be available on the website to members, and we'll be sending out that login to you as well. But Steve, and then if there's additional questions that are coming through that we don't have time for, like Steve mentioned, you can email him or you can email me and I can get them over to Steve. But Steve, I've got this one question for you.
Sure.
In the case of the poor control loop tuning example, what comment would you make to the controls contractor? Would you suggest a solution or simply ask them to review and address the tuning?
Repeat the first part. You're talking about the three.
In the case of the poor control loop tuning example.
Oh, the poor control loop tuning example.
Yes.
Yeah. Well, I mean, that would come out. I mean, the way first we would catch that during functional testing. Okay, and we would assign that as an issue to the controls contractor to be resolved. And then we always, pretty industry standard, we include 2 rounds of functional testing. So we would tell them, look, you know, your loop's not tuned right. We're going to come back out on our second round of testing. You need to tune it right so we get a good response. And we would fail it. we would come back out during the second round. Hopefully they address the issue and could demonstrate it's been tuned correctly, and at that point we would pass it. If it's still an issue, after 2 rounds of testing, our policy at our company is to charge the client, whoever contracted us, for our additional time and ask that they back charge the responsible contractor. But we would not, any loop tuning that we caught that was not working correctly, we would not leave it that way with the client. We would oversee the resolution of that loop tuning on behalf of our client. I hope that answers the question. We don't see a lot of loop tuning issues. I mean, we see some, but we see tons and tons of this stuff. Just slide after slide of stuff that doesn't make sense. And then you got to figure out, why doesn't it make sense? It could be installation, it could be the design, and my experience is 80% of the time it's controls. 20% of the time it's somebody else's fault, but 80% of the time it's controls, and that's why it's so important to have a strong controls background to be a commissioning provider.
Great. We might have maybe time for one more question, if that's okay, Steve, if you're good with that.
Sure. Of course.
How do you recommend that the graphics best be verified? 106 is 207, etc. Also, it seems like many of your examples are based on rules of thumb that might be programmed into automatic FDD software. Do you use? Yeah. So go ahead.
Okay. So an interesting question on the graphics. How do you recommend they be verified? If you're in early enough, I teach a class on direct digital control system design, and there should be 3 parts to the design. There should be a flow diagram, a sequence of operation, and a points list. And on the points list, it should list all the inputs and outputs for the system, and the ones that should appear on the graphic, there should be a column there that says appears on graphic, and if there's a check there, that point should appear on the graphic. So you can use that design, which later becomes a submittals, which then you can verify the graphics and say, look, on the points list, it shows that the chilled water return temperature is supposed to be on the graphic and you don't have it there. You need to put it there. The problem that you got to be careful of is, you have to have a third thing to reference so that the controls contractor can pass or fail your test. It can't be just up to whatever he wants. It has to be the design and then the submittal, and then his actual installation has to match the submittal. So that's how I would verify the graphics. There was a second part to that question. What was the second part?
Seems like many of your examples are based on rules of thumb that might be programmed into automatic FDD software. Do you use?
Okay, so
go ahead.
I mean, I'm not exactly sure what you're referring to as rules of thumb, but I guess the way I would speak to that is everything needs to be testable and verifiable. And if you can't test it, it's not done. It's not complete, whether that's the design or whether it's the submittals. So going back to this, the design has to be complete where there is no unknowns. There's no leeway for the controls contractor to do what he wants. And even if this isn't complete, even if you come in after the design's done, the submittals need to be 100% complete. I need to know exactly if there's duct supply air pressure reset. What's the algorithm? How is it supposed to work? Is it looking at the damper positions of the downstream VAV boxes, or is it looking at the number of calls for cooling? If I don't know that, I can't test it. So you have to know every piece of code that's being written for that project. You have to understand it so you can test it, because any piece of code that's being written for that project could be a point of failure. And if you don't check it, what value are you adding as a commissioning agent? So it's really important that anything that's custom programmed for that project is testable.
Great, thank you. And Steve, one final question. Can you elaborate on why you would suggest using a 1-hour trend data interval? With that interval, wouldn't it be difficult to identify poor control loop stability?
Okay, so trend data is normally not a good source to check out whether a loop is, well, it can be. I like 1-hour intervals because if you do too short of an interval, one, you clog up the network because all of that data has to get communicated from the controller that's collecting it to the supervisory controller or the server that's storing it. And if you, let's say, trend every minute and you have 50 trends, you kind of clog up the data. The other thing is usually the storage is a moving window of data points. So if you do 1 hour, you could probably hold a week's worth of data, which is valuable. Whereas if you do 1 minute, you could only hold 1/60th of a week's worth of data. So it kind of depends what it is you're trending. If it's something that you wanted to trend that you don't trust, let's say it's something that changes really fast, like a supply air duct static pressure loop. You don't really, I mean, that's kind of a silly example because you could just look at it during functional testing to know if it's working. You wouldn't need to trend it. Most things change relatively slowly in HVAC, like room temperature. Even if you start supplying 55-degree air or 90-degree air, it's going to take certainly several minutes and potentially hours for that room temperature to change. And trending it, every minute, every 5 minutes, you're clogging up a lot of data and you're reducing the number of data points to get a good graph of what's happening. So 90% of the things that you care about, an hour, I think, is the ideal interval to balance the amount of data points you're going to get, not clogging up the network and still seeing what's going on.
Well, thank you, Steve. I think that's all the questions we have at this point. We really appreciate your time today. And on behalf of the BCA, I'd like to thank everyone for your participation in today's Tech Talk. Have a great day, everyone.
Thank you. And again, you can reach me here if you have any follow-up questions.
Thanks, Steve.